I am Dr. Vemula Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series of Atomic and Molecular Spectroscopy. Today we are going to discuss spectroscopic terms for multi-electron atoms, such as whenever electrons in the SPD or any other orbital, that means more than 2 or 3 electrons. Okay, so first let us find the spectral terms for p electrons, such as p2. Whenever we consider 2 electrons in the p orbital, same p orbital, that means here the value of principal quantum number n and the value of L, that means orbital quantum number L, are same. Both values are same for the 2 electrons. That means by following the Pauli's exclusion principle, the two values, ml value and ms value, must be different for the 2 electrons. These two values should not be same for the 2 electrons. So here let us assume that we apply or we placed the atom in a very strong magnetic field where all the internal coupling are broken down. Okay, that means spin angular momentum and orbital angular momentum will broken down. In general, whenever it is in the absence of external magnetic field, the spin angular momentum and orbital angular momentum add up and give the total angular momentum J values. So here we are applying the strong magnetic field where all the internal coupling are broken down. So the individual L bar and S bar vectors then makes precision around the magnetic field independently. Orbital angular momentum and spin angular momentum makes precision around the applied magnetic field individually. Okay, so the quantized component of orbital angular momentum and spin angular momentum can be taken as ml h by 2 pi and ms h by 2 pi respectively. So in general, for p electron, the value of L is 1, so that the value of ml, orbital magnetic quantum number ml, can be taken as 1, 0, minus 1. So 3 possible ml values are there for the electron, p electron. Among the 2 p electrons, there are 2 p electrons in the same subshell. Okay, so those 2 p electrons, each one can have any of these values, 1, 0, minus 1. So, and again, those 2 electrons can have ms values, plus 1 by 2 or minus 1 by 2. Any of these 2 values can be existed for the 2 electrons. And again, we should remember that the 2 electrons cannot have the same ml and ms values for a particular instant. So those 2 values, ml and ms values, must be different for the two electrons. Okay, so these are the possible combinations of Ml and Ms values for the two electrons. For example, if particular electron, among the two electrons, there are two electrons P2, so electronic configuration P2, either the principal quantum number is 2 or 3 or 4, whatever the principal quantum number, but the two electrons are in the same orbital. So n value is same and L value is same for the two electrons. So to satisfy the Pauli's exclusion principle, the Ml value and Ms value should be different. These two values must be different for those two electrons. Okay, so these are the possible combinations. For example, if one electron, in particular electron, is having Ml value 1, Ms value 1 by 2, the second electron cannot have the same values of Ml and Ms, 1 and 1 by 2. It should be have other combination, other value among these combinations. One electron with these values, then other electron should have values either 0 1 by 2, minus 1 1 by 2, 1 minus 1 by 2, 0 minus 1 by 2, minus 1 minus 1 by 2. Okay, so if one electron is in the state A, let us give some combination name for combinations A, B, C, D, like this. So you may call as if the electron is in particular having particular values, Ml values 1, Ms value 1 by 2, then the state is represented by A. This is the state, B state, C state, D, E, F. So there can be 6 different states for any electron. Okay, 6 different states. Electron can be in any state among all these 6 states. So if one electron is in particular state A, then the second electron cannot occupy this particular state A. It should be in the other states, any of the other state, B, C, D, E or F, any other state. Okay, so for example, if the second electron is in the B state, first electron is in the A state and second electron is in the B state. So that is the situation when the two electrons, one is in the A state and the second electron is in the B state. That is a particular condition or situation. Otherwise, second electron may be in the C state, not here, maybe here. So AC is another combination. The electrons can be existed. So that is also one state of the electrons to be existed. Otherwise, the second electron may not be in the C, or it can be having in this situation, this condition. That means Ml value of the second electron is 1 and Ms value is minus 1 by 2. Then the combination of those two electrons, one is in A state, one is in the D state, AD. So like that, there could be some particular number of combinations. Okay, these are the states of electrons. There are 6 possible electron states for those electrons in that atom. Okay, so there are, I'm seeing and observing all these states. the two electrons with uh, two electrons, two combinations of these states are required, and electron states should not be same, so that there could be 6C2 number of combinations without any alike, with no two alike. Okay, because 6C2 means combination, possible combinations is 6C2. So 6C2 means 6 factorial by 2 factorial into 6 minus 2 factorial. That means 6 into 5 into 4, 3, 2 into 1, 5, 1 into 2, and 4. 4 means 4 into 3 into 2 into 1. So you can cancel here. 2 3s are 6. So there are 15 such type of combinations, among which there is no two electrons can have the same values of ml and ms values. Okay, so we can easily identify those combinations also. If an electron is A, second electron may be in the B state. Okay, if one electron is in the A, second electron AC. So this is also one combination, possible combinations. Like that, we can take AD, AE, AF, and BC, BD, BE, BF, and again, and also CD, CE, CF, DE, DF, EF. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Total 15 possible combinations are there. So whenever these possible combinations exist in the electron atom, then mutual interaction occurs between orbital angular momentum and spin angular momentum. So we need to add up two values of ml to obtain the strong field values of ml, and also the values of ms are added to form the strong spin magnetic moment ms. Okay, so whenever the electrons are in the states, one electron in the A state and one other electron in the B state, then orbital angular momentum add up and spin angular momentum add up individually, so that the values of orbital angular momentum 1 1, because ml value in the A state is 1 and ml value in the B state is 0, so that the total ml value 1. Okay, again the spin magnetic moment, this is having 1 by 2 for B state 1 by 2. So total spin magnetic momentum quantum number becomes 1. So in this way, in those 15 conditions, among those 15 conditions, we can find out the total orbital angular momentum quantum number and spin magnetic quantum number ml and ms values as shown in this table. these values are obtained by adding the ml values in those two states and ms values in those two states. Okay, like this we are getting all the values. So if you observe all these values, we can identify that the highest value of ml, we can take these values are ml and these values are ms. So among all these values of ml, the highest ml value is 2. Highest ml value is 2. Okay, so it indicates deta, total orbital angular momentum quantum number ml is equal to means deta, and ml can occur only with ms equal to 0. ms equal to 0. The ms value here in this table is 0. And again, except apart from this ml equal to 2, we are obtaining ml value 1 0 minus 1 minus 2, which belongs to the same term and having ms value 0. So all these terms also indicates d term. D term. Okay, so out of the 15 combinations, these following combinations form the 1D term, because since s equal to 0, the multiplicity is equal to 1 and the term is d. 1D is the term for all these combinations: AD, AE, AF, PF, CF. So that means 2, 1, 0, minus 1, minus 2 ml values, and ms value is 0. So all these terms forms the 1D term. Here multiplicity as ms equal to 0, ms equal to 0. And again, multiplicity we are indicating it as capital M is equal to 2 into s. S means here 0 plus 1. That means 0. Multiplicity is 0. And L value is 2, so that the term is 1D. Okay. So and the remaining terms, the remaining combinations, there are 5 states having the 1D term. Okay, let us see the remaining combinations apart from those 5 states. The highest value of ml is 1 among the remaining combinations, and for which if we take for which ms is 1, then these values must belong to 1p term. Okay, because L equal to 1 and S equal to 1. Okay, and L equal to 1 means the ml values can be 1 0 minus 1, and S equal to 1 corresponds to ms equal to 1 0 minus 1. So for all those combinations for which ml equal to 1 0 minus 1 and ms 1 0 minus 1, that belongs to the term 3. Okay, so these are the combinations, possible combinations having those ml and ms values. So 1 0 minus 1, 1 0 minus 1, 1 0 minus 1 for ml values, and ms values 1 0, -1. So here L equal to 1 and S equal to 1 for these states. So as S equal to 1, the multiplicity 2s plus 1 means 2 into 1 plus 1, that equal to 3, and as L equal to 1, that indicates the term P. So 3 is the multiplicity, P is the term, 3P is the term for all those states of electrons. Okay, so and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 combinations forming this 3P term. Okay, in the earlier slide, the term 1D is formed by 5 combinations. Now it is 9, and 5 plus 9 means 14. And the remaining combination left, for which ML equal to 0 and MS equal to 0. So among the 15 combinations, if you see here, among the 15 combinations, ML equal to 0 and MS equal to 0 for BE term, BE combination. BE combination. So it gives the term 1s. As ML equal to 0, MS equal to 0, that means total orbital angular momentum is 0, total spin magnetic momentum is 0. That indicates that forms the term 1s. Okay, so the two equivalent p electrons gives rise to 1d, 3p, 1s terms. Okay, the fine structure levels of these terms can be written as 1d2. Why? Because the 1d s equal to 0 and d equal to 2, that means L equal to 2, then J value you can obtain as 2. So 1d2. Here in the term 3p, s equal to 1 by 2, s equal to 1, s equal to 1, and L equal to, here s equal to 1, L equal to 1. So J values are 1 minus 1 to 1 plus 1, that means 0, 1, 2, 0, 1, 2. So the fine structure becomes 3p 0, 1, 2. J values are 0, 1, 2. And here in the term 1s, s equal to 0, L equal to 0. So J value is 0 plus 0, 0. So the term is 1s naught. So that the file structure levels are 1d2, 3p012, and 1s naught. And if we observe the states of electron for the non-equivalent electron configuration are like this. Whenever we see spectroscopic terms for non-equivalent electrons, these are the terms 1s, 1p, 1d, 3s, 3p, 3d. But for equivalent electrons, we are missing 1p term and 3d term. 1p, 3d, and 3s also. these are the terms we are missing for the equivalent electrons. We are observing only 1s, 1d, and 3p. These three terms are only existing for the equivalent p electrons. And again, we can also say that these terms are also exist for the p4 configuration also. p4, when the electron configuration p4, then the same terms exist for this configuration. Why? Because the maximum number of electrons that can be filled in p subshell is 6. Here we are finding the spectral term for p2. Here p4 also can have the same terms as those for the p2. So these terms are also same for the p4 electronic configuration. So that means 4 electrons in the same subshell p. Okay, so this is the procedure to find out the spectral terms for two non-equivalent p electrons. Okay, so these are the references. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.